Okay, let's continue with the afternoon session. So the next speaker is Weinan Zhang from Hong Kong, and he will talk about Drinfeld type presentations for twisted Yangians. Let's welcome the speaker.
Yeah, thank you for the introduction, and thank the organizer for giving me the opportunity to speak here. So today I will talk about a new presentation for twisted Yangian. This is joined with Kang and Weiqiang Wang. So first I will briefly review two presentations for Yangian, R-matrix presentation and the Drinfeld presentation. I guess most people are very familiar for this part. And then I will review R-matrix presentation for twisted Yangian. And then I will talk about our formulation of Drinfeld type presentation for twisted Yangian. Okay. So we start with the standard R-matrix. And here you think it's an operator on V tensor V. And the action of P is by swapping two components. So they satisfy this Yang-Baxter equation. And we already see a variant in Appel's talk. And the Yangian is an algebra with generator Tijr subject to the following relations. So again, here you wrote these generators in the generating function, and then you put them in a matrix. So then the defining relation is given by this RTT relation. Okay. And you can look at the entry for each set, then you will get a bunch of defining relation. And this is a compact way to write. And so the Yangian for SLN is just quotient by the center. For other classical type, you can also define the Yangian using an R-matrix presentation. In that case, the R-matrix is more complicated, but the defining relation is still something similar to the RTT ones. And also, the Yangian is a hope for algebra deformation of the current algebra. For example, you can think this Tijr is a deformation of Eij u to the r. And also the product, the formula for the coproduct is given by this. Okay, so the second presentation is the Drinfeld presentation. So here we start with the Cartan matrix and the Chevalier generators for G. So then the Yangian is generated by this element subject to the following relation. So here you can think this kappa is a deformation of Hi u to the r, and psi plus is a deformation of this positive part, and psi minus is the negative part. Okay. So first, let's see. This kappa, they form a commutative subalgebra. And the net-way relation you see is similar to the case of the algebra. And in the next two relations, this is a flavor of deformation. So here, the curly bracket means the anti-Lie bracket. So AB. And the last one is the cell relation. Again, in this case, you have plus or minus. So in this relation, you either take all power to be plus or all power to be minus. Yeah, so this is the Drinfeld relation. So this presentation is of fundamental importance in the theory of Yangians, and it has application in representation theory and intergroup system. I mean, okay, so now we want to review, how to show these two presentations are equivalent. So this is use a method called Gauss decomposition. So in this case, we write the matrix T as a product of three matrices. This is unipotent lower triangular, diagonal, and unipotent upper triangulars. So then you can identify the generating function of psi with this EI plus 1. And this upper triangular entry can be written in terms of R matrix generators. So in this way, you will have a way to write a Drinfeld generator in terms of R matrix generator. And there is a similar for cosine minus. And for kappa, it's given by this formula. So now, once you identify the generators, you have a map from the Drinfeld presentation to the one defined by R matrix presentation, and then you verify the defining relations are satisfied. Yeah. Sorry, say again. Oh, yeah, yes. So this is just an example, but you can do it for general sense. Yeah. Okay. Yeah, of course, in this way you can verify you have algebra homomorphism, and it's an isomorphism because you have some PBW basis. Okay, so this isomorphism was stated by Drinfeld, and if you want to look at a detailed proof, then you can look at Brown-Dunn and Fleischer paper for type A, and for type BCD, you can look at Jean Liu Morley's paper for details. Okay, so next we look at the twisted Yangians. The twisted Yangians are defined for symmetric pairs. So we let theta be an involution on G. So that's order 2 automorphism. And this is called a symmetric pair. So G theta is a fixed point subalgebra. For example, for type A, you have these 3 kind of symmetric pair, A1, A2, A3. And in this case, we can lift theta to the current algebra by using the following formula. So in other words, the theta check, it sends U to minus U. Okay. And so the twisted Yangian is a coideal subalgebra of Yangian as a deformation of this fixed point subalgebra. So I will call this fixed point subalgebra in the current algebra as the twisted current algebra. Okay. So the twisted Yangian was introduced by Olshansky for type A1 and A2, and Morley and Rabisi for type A3. They also call it the reflection algebra. And for type BCD, it's introduced by Gui and Reguletsky. So all of these definitions are in terms of the R matrix presentations. So one of the motivations to introduce twisted Yangian, because they provide solutions of reflection equations, which are important in integrable systems with boundary conditions. I think I should also put Professor Shirendik's name there. Okay. Yeah. Yeah. So let's, for example, in the type A1 case, the twisted Yangian is a subalgebra generated by this element, and this Sijr are defined by this equation. So if you look at the entries, matrix entry for right-hand side, it will tell you a way to write Sijr in terms of this Tijr. So then you have some more subalgebra. And the twisted Yangian admit a generator relation presentation. This is called the R matrix presentation. So the first relation is the reflection equation, and the second relation is the symmetric relation. Okay. And again, if you apply the coproduct to the twisted Yangian, it lies in the Yangian tensor twisted Yangian. In other words, this is a coideal subalgebra. Okay, now we have this R matrix presentation for twisted Yangian. The natural question is, what are the Drinfeld presentation? Although this R matrix presentation has been known for more than 30 years, the Drinfeld presentation is only obtained very recently. So in this talk, I will talk about the split type. So here, split means the involution theta is a Sharlane involution. And in the type A case, split just means type A1. Actually, for each the algebra, there is a symmetric pair of there is a unique symmetric pair of split type. And the split type is our, how to say, This is the part which we have finished. And before our work, Jonathan Brown obtained some kind of presentation for this lower rank case. So his approach is by brute force, and the presentation he obtained is also very complicated. So our approach is independent of his one. Also, his approach is hard to generalize to higher rank. Okay, so first let's take a look at the twisted current algebra. So here we look at the Sheva-Lin-Yong So it swaps EI and minus FI and send HI to minus HI. So then we can have a KP decomposition. So here K is the fixed point subalgebra, P is the -1 eigenspace for omega. And then because when we lift the omega, U is sent to minus U, then if you look at the fixed point subalgebra, this KP will alternating. And then we can write down a bunch of current generators for this twisted current algebra. So because here we are mixing EI and FI, so then you only have one series BIR here. So they lies in the fixed point subalgebra. And for the Kang part, note that you only have this TIS for SR. Because if S is even, then TIS is just 0. In other words, only for this R degree, you have this Kang part. Okay, so as a deformation of this twisted current algebra, we have a formulation for the Drinfeld type presentation for twisted Yangians. So first, let's look at this presentation, and later I will tell you how we obtained it. So we start with the Kang matrix, simply list. And we can define a complex algebra with generators HIS and BIR. So actually for generators, you only need HIS for R the S. But for convenient, you still include all indices and set the even ones to be 0. So in this way, you can write some relation in a much simple way. And so let's look at these relations. So first, this HIS, they form a commutative subalgebra. And the second relation is similar to the case of the algebra. And for the next one, so note that the sub-index, for example, for H, they jump by 2. So it's from R-1 to R+1. And in the case of Euro-Yangian, the index only jump by 1. The reason why it should jump by 2 is also related to this parity on the Kang part. And so then on the right-hand side, you also have a second term. Okay. And for the next relation, if you only look at these first 3 terms, then it's similar to a relation in the case of Yangian. But in this case, because your B involves both F and E, so then when you do bracket, you should also get some Kang part. So in other words, you can think this relation is a hybrid of 2 relations in the case of Euro-Yangian. Okay. And the next 2 relations are the cell relation. In the case of Euro-Yangian, the right-hand side of cell relation is 0. But in this case, you have some non-zero term. Actually, determine this non-zero term is one of the technical part in our work. Okay. Okay, so now you may wonder, so we proved that in the type A case, this new algebra is isomorphic to the twisted Yangian defined in R matrix presentation. So the proof of this theorem is still using the standard method, using the Gaussian decomposition. So here you do the Gaussian decomposition for the matrix S. And in this case, you can actually identify this positive part and the negative part. So here fi plus 1i equals ei plus 1 with some parameter shape. And this will give you one theory, that's your bi. And for the Kang part, you still have a formula similar to the Euro-Yangian case. And then you have a map from this new algebra to the twisted Yangian. You verify its algebra homomorphism. And the verification of this defining relation in this case is much complicated than the case of Euro-Yangian. And again, the isomorphism follows from some PBW theory. Slide back. Yes. Okay. Okay, so now this is the type A case. So how about other type? So actually, for other type, we also have a formulation of this new algebra. For example, for the simplest type, you say you just change the Kang integer. And for the non-simplest type, in our second paper, we have a formulation. In this case, you have several more cell type relations for Cj equal -2, -3. And for type BCD, we expect that our new algebra is isomorphic to the twisted Yangians, but we haven't proved it. The difficulty is that if you want to do Gaussian decomposition for type BCD, technically it's harder. So this part we haven't proved it. And for the exceptional type, actually the twisted Yangian has not been defined. You can use our presentation to be a definition for this twisted Yangian. Also, you can even define so-called affine twisted Yangian by plugging in the affine Kang data. And this is for the split type. In a forthcoming paper, we will have a formulation for the quasi-split type. So quasi-split means we consider involution of this type. So it's a Shevardin involution composed with a Dinkin diagram involution. If tau is the identity, then you go back to the split type here. Okay. So now I will explain how we obtained it. That's related to this affine I quantum group and quantum symmetric pairs. So in this case, we look at the untwisted affine algebra. And we can lift an involution on G to G hat by using this formula. So in this case, it sends T to T inverse. So there is a quantization of this symmetric pair called a quantum symmetric pair. And this also mentioned in Appel's talk. This quantum symmetric pair was introduced by Lester and Kolb. Actually, it can be defined for arbitrary Kazhumudy type, but in this case, we only need this affine type. So here U is the Drinfeld quantum group associated to affine algebra J hat, and UI is a coideal subalgebra of affine quantum group. It's called affine I quantum group. Okay. So we know this affine quantum group is closely related to the Yangians. That means the Yangian can be recovered from a affine quantum group by a process called degeneration. So if you start with the Drinfeld presentation for affine quantum group and you do degeneration, you can get the Drinfeld presentation for Yangian. And in the case of quantum symmetric pairs, we also obtained a Drinfeld presentation for this affine I quantum group. So this presentation was the first obtained by Lu Ming and Wang for split ADE type. Myself generalized their work to split BCFG. Actually, we also generalized this Drinfeld type presentation to some quasi-split type. So then we just apply a similar degeneration method to the Drinfeld presentation for a affine quantum group. And then we can obtain the Drinfeld presentation for twisted Yangians. Yeah. So in the end, I will mention some more applications. So the first application is about this. Once you have the Drinfeld presentation, you can define so-called shifted twisted Yangian. And we expect it's related to the finite W algebra of type BCD. For finite W algebra of type A, its relation to shifted Yangian is already established by Brownon and Klashev. And
can I ask, what is the paper by Tapiner and Topley? What do they state?
This one is just obtained they just posted it last month. They did a semi-classical version of this one. So roughly speaking, you need to consider some semi-classical limit of shifted twisted Yangian, and that can be identified with some slowly slice in type BCD. Yeah. Also, I think Weiqiang and his collaborator is working in this direction, maybe on a different, slightly different problem. Also, because this Drinfeld presentation provides you a commutative subalgebra, you can use it to construct characters for finite dimensional modules of twisted Yangians. This is a generalization of Yangian character. And we also expect it has application in integrable system with boundary conditions. And we also expect this Drinfeld presentation has application, has a geometric construction. Yeah, so that's the all of my talk. Yeah, thank you for listening.
Questions or comments?
Yeah.
So can you go to the slide last in twisted Yangian series? Last two. No. Again.
To the presentation.
Last in twisted Yangian. Last slide in section of twisted Yangian.
Okay.
Yeah. Can you comment the form of E and F matrices? So you say that it looks like that E matrices it's transposed to F matrices. Is it true? Transposed and change sign.
Yes. Yeah. Because. How to say this? You can think you have some symmetry. You have some symmetric relation in this.
I don't mind. So the statement. So S has form upper diagonal matrices F times D that is commuting diagonal elements, and E which with up to some transformation of parameter is nothing more but transposition of F, which and becomes lower diagonal.
Let's see. Yes, so certainly you need some work to show this relation. Yeah, it's not how to say, it's not directly from the symmetric relation. You need some.
Yeah, but you said that F is the same as E.
Yes.
And F is upper diagonal one.
Yes.
Amazing. And maybe another question in discussion. Can you go further?
Which page?
Second in discussion section. Second slide in discussion section. Next one. Yeah, third. Not next one, sorry. This, about this. Okay. So you say that you can consider the use twisted Yangian and you can degenerate it to usual Yangian.
No. We start, so this degeneration is from this I quantum group. It's a subalgebra of a affine quantum group. And you apply degeneration to I quantum group, you got twisted Yangian.
From affine to Yangian. Both.
Yeah.
Both. With the commuting diagram, essentially.
So how twisted algebra connected with Yangian? Not twisted algebra. Can you explain? What do you mean? I mean, what do you state? I have Yangian G in up this first line. Y of G is Yangian.
Yeah, this is the Euro Yangian, and this curly Y is the twisted Yangian.
So what's the statement in the first line?
The first one is you from a quantum group to Euro Yangian. Yeah. The second one is you from
so it's
affine.
Okay, I understand.
Yeah,
Thank you.
Any more questions?
So thank you for good talk. So I remember in type A, Blunt and Kuleshev were making a lot of presentation called parabolic presentation to making a connection to isomorphism of shifted Yangian of type A to finite W algebra of type A.
Right.
And can you also construct such a parabolic presentation in type BCD?
Yeah, that's a very good question. So we haven't done that part, but I think Weiqiang and his collaborator is already started working with it. Yes. So this is a very natural question. Yeah.
So, and also you constructed other twisted Yangian, or maybe type G or F or something like that.
Right.
And can you also expect making some isomorphism between the finite W algebra of such a type?
So for the exceptional type, the twisted Yangian is not even defined in arithmetic representation. So then, so you cannot talk about isomorphism in this case. Yeah.
Thank you.
Okay, one more quick question.
You had a formula that's been known for a while, the triangular factorization of the Yangian, the T matrix. In the classical case, this is the Gaussian pointwise Gaussian decomposition of T of U. But we know that not all matrices admit Gaussian decomposition. There are there is a singular decomposition. There are singular cells. What would be the Yangian quantum counterpart of this fact?
So I don't really know what's the counterpart for twisted Yangian.
Okay, thank you.
There's time for another question. The speaker finished on time, so there's time for one more question. Yes.
So the Gauss-Toledano-Laredo, they prove more than the generation. They actually prove that there is an isomorphism essentially up to completion. In particular, also the category representation is the same. So do you guys have some reason to expect one way or the other?
Oh yes, I think a similar statement for twisted Yangian can also be made. So loosely speaking, you can embed this affine quantum group into a completion of twisted Yangians. Yeah, and that generalizes the work of Gautam and Laredo. Yeah. Yeah,
okay. Let's thank the speaker again.